Okay, so let's talk about Constexpr. So in C++ we have templates, which are very commonly used to write generic code. And generic code usually refers to functions or classes which accept arbitrary types or can operate on a range of different types. A few years back, however, it was actually discovered that there's more to templates than meets the eye. Templates are actually Turing complete. This means that theoretically you can compute anything that is computable with templates, and this will always be evaluated at compile time. So this was very useful for people who wanted to simplify their programs and optimize them so that important values were computed at compile time rather than at runtime. So for instance, you might have a table that you would like to populate with hashes, and you could do this at runtime, or you could fill it in by hand, but either of those solutions are not ideal, so you could do it with template metaprogramming. Template metaprogramming is what the realization that templates are Turing complete gave rise to. And template metaprogramming, it's very useful, but there's a few issues with it. So for one thing, I'd love to show an example of some template metacode here on the slide. However, one of the main problems with template metacode is that it's really damn long. It's often very lengthy and it's incredibly hard to read. So I encourage you to go look up an example of it. You'll see that even the smallest examples are often a couple pages in length of header, and it's not really ideal for one thing. It's also kind of slow, and we haven't talked about Constexpr yet, but suffice it to say that Constexpr kind of dwarfs template metacode in most situations in terms of running time. So in C++11 we have this handy new keyword called Constexpr, and what Constexpr does is it indicates that the value of a function can be computed at compile time. Now, in a lot of ways, it's not really a guarantee that something will be computed at compile time, but there are certain situations where it is guaranteed to be computed at compile time. So, for one thing, if you have a context that requires a compile time constant, and you supply it with a constexpr function, then that constexpr function will be evaluated at compile time and used. So for instance, if you need to supply a value to a template argument, you can supply it a constexpr function, and that will be evaluated at compile time, and that's guaranteed. However, in other situations, it's not guaranteed to be computed at compile time. So in a lot of ways, it's like inline. It's more of a hint than an actual guarantee. But this is actually a lot more versatile than template metacode. Template metacode is really only good for doing things at compile time. Constexpr functions, you write one version of a function. It's using the exact same syntax as normal C++ that you're already used to. Template metacode, that's not the case. It's kind of like a different language. But with Constexpr, you write one version of the function, and you can use it in contexts where it will be computed at compile time, or in contexts where it will be computed at runtime, and that's totally fine. One version of the function. Much more ideal. So here we have some example code that illustrates Constexpr. So we have this function fac, which is it computes the factorial of a number. Simple recursive function. So you'll notice that we have this one return statement, and at least in C++11, it is a requirement of Constexpr functions that they only have one return statement, among other requirements. So I have this ternary operator here to kind of boil it down to one return statement. So you'll see here, if I can draw your attention down to this printint function. So this accepts a template argument, which allows us to, down here, invoke the printint function with fac as a template argument. So since we're supplying it to a template argument requires a compile time constant. So it is guaranteed in this context that fac will be evaluated at compile time. On the other hand, you see down here, this is a situation where fac will be computed at runtime. And we are creating this variable u, this int u. We are marking it volatile so as to disable optimizations. And since optimizations are disabled, the compiler will have to evaluate this at runtime. If u was not marked volatile, then there is actually a chance that the compiler will be smart enough to decide that, okay, I can evaluate this at compile time, so I will. But by marking it volatile, we are disabling those optimizations. And so in this context, it is guaranteed that fac will be computed at runtime. The versatility of Constexpr is that we can use Constexpr functions for both situations, so incredibly useful.